Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we're going to be talking about climates and changing climates and focus both on natural causes of climate change as well as how we as humans are influencing our atmosphere and climatic conditions. There we go. So, we'll begin kind of focusing on then factors that influence the climate, and we'll move into what's known as the Köppen climate classification system. We'll explore scientific evidence on how we can reconstruct past climates, and then finally end today's lecture, where we'll talk a little bit about how we as humans are influencing climatic conditions and what that potentially means for the future. So, before we begin, what is the difference between weather and climate? Well, weather is the state of the atmosphere, like right now or in a short time, so short temporal scales or at a certain place on Earth, where climate are long-term average conditions, such as temperature and precipitation. So it can define kind of what to expect for an area, so weather over time. So then the study of weather and climate largely falls into these categories as meteorology, which a meteorologist studies the short-term atmospheric phenomenon, which ultimately makes up our day-to-day weather and our near future forecasts. And so we listen and watch our meteorologists on the news and on the radio, and those meteorologists, again, are very much concerned with the present and near future, where a climatologist then is studying geographic distribution and characteristics of Earth's climate over space and time. And so now we're thinking much broader spatial scales, and as well as long temporal scales. Can you think of two factors that influence climate and then describe how they influence climate? So environmental factors, what conditions on Earth have we learned about in maybe Earth-Sun geometry? And so think radiation has the hint. And so our latitude then has a lot to do with insolation, incoming solar radiation, as we previously explored in great detail in this class, thinking about that location of the subsolar point. And so just generally speaking, latitude has major divisions of climate. And so near the equator, near the subtropics, into the mid-latitudes, and then further north or further south toward the North and South Pole. And then beyond just these kind of broad latitudinal differences related to insolation, we can then kind of even subdivide within those regions and think about seasonality and extremes of temperature and or precipitation, and perhaps patterns that come and go, like cold and warm, or rainy seasons and dry seasons. So some additional factors that are really important in terms of how and why climates and where climates exist on Earth include previous content we covered, such as air mass circulation. So thinking about our air mass patterns and our trade winds, so locations on Earth that have these dominant wind patterns like the westerlies or the northeast trade winds, for example, and then those are creating these kind of like long-term persistent and consistent conditions. And so because of that, those air mass circulation patterns help to create climates as we know them. And then kind of scaling in toward a continental perspective, we've also previously covered how locations near a large body of water, like the Atlantic, versus more interior continental locations can have dramatic influences on radiation and temperature, and therefore also if influencing long-term average temperature as well as precipitation conditions due to the proximity of lots of moisture, or rather how far away you are from lots of moisture. And then here, at least last but not least, at least for this examination of major climate factors, topography can have and most definitely does have a very dramatic influence on both weather and then long-term conditions. And so we'll explore later these highland climate variations and we kind of go up altitude and elevational profiles. And so depending on your relative location on the windward or the leeward side, and then really even kind of like latitude, but we can subdivide into elevation. There are major elevational bands or gradients in large mountain ranges that have expected weather, climate, and ultimately also biota, so biomes. All right, so we're going to explore the most common climate classification system, which is known as the Köppen climate classification system. It is subdivided into major categories, and these major categories stem from the relationship between major vegetation regions around the world with regional climate characteristics. So areas that are persistently hot and dry or hot and wet versus areas that are cold and dry, or perhaps moderate and wet. And so let's think about that in greater detail. And as I kind of just alluded to, and as is defined here, the separation of these major categories and then the subdivisions, as we'll learn even more in greater detail, are based upon long-term average monthly temperatures, long-term average monthly precipitation patterns, and then you can compare these monthly patterns to annual averages, and that then allows us to think about seasonality as well, as your average temperature could be 45 degrees Fahrenheit, and in some climates they might have really hot and really cold. In other areas it might be 45 degrees Fahrenheit more or less all year long. And so that variability also plays a factor, or is at least considered here as we classify climates. And so here are the six major climate classification groups, and they are denoted with these letters A, B, C, D, E, and then H for Highland climate systems. And so we'll go through each of these major categories. And for this course and quizzes and exams, I will encourage you to be able to compare among these major climates. And I'll go through and there'll be a slide dedicated to each of these, like tropical climates, for example, and we'll then compare among them. I do want you to appreciate that within each of these major categories, there are multiple subdivisions, and those subdivisions are based both upon temperature and moisture. And while we'll explore this here within this lecture and within the course, at least for quizzes and exams, I'll largely just kind of focus here on comparing our major climate classifications. And so, as I already kind of previously introduced, these climates range from tropical to highland, mid-latitudes, and largely the major divisions between these six groups are based upon temperature, and then thinking about seasonality of temperature as well as moisture attributes allows us to further kind of classify within each of these major groups. So a map here then of the Köppen climate classification system. I did want to make a point just that here's Vladimir Köppen, the originator of the Köppen climate classification system. I like to include those old photos sometimes. All right, so this is broadly what the climate, or where these climates as tropical, microthermal, mesothermal, arid, polar, and highland. And again, I'll have a slide dedicated to each of these major categories. But for now, just appreciate that we can look at these major climates like tropical and red and light red, pink, here kind of occupying near the equator, and these broad zones of climates. Another way to kind of appreciate these major categories, as we described, they're really based upon temperature as well as precipitation. And so this is more of a conceptual figure, but we can think about colder temperatures and increasingly warmer and warmer and warmer, and then low precipitation to high precipitation. And then we can think about our highland climates, and then for the remaining five categories, from hot and dry to hot and moist to more moderate, humid tropical, or sorry, hot and moist. So anyways, we can kind of separate them here. I won't quiz you on this figure or anything, but I think it's a nice way to just appreciate this kind of like scale of both precipitation from dry dry to wet, and then from lower temperatures to higher temperatures. All right, so let's begin our kind of singular examination of each of these major climates. So our tropical climates are exist on planet Earth from 25 north to 25 south latitude, so plus or minus near the equator, where we receive consistently lots of insolation and it is consistently warm as a result of that. And so these equatorial regions then can be further subdivided based upon their precipitation categories. And so areas that are hot and moist can support this incredible amount of vegetation, which is really cool, a tropical rainforest, right? And so to be warm and wet, you can have like a tremendous amount of biomass can grow. And so here our subdivision as A little f is a tropical rainforest, where other regions in this kind of lighter middle blue condition here as AM also receive at certain points of the year, they will receive tremendous amount of precipitations. However, other portions of the year, they receive very little to no precipitation. So there's this kind of really dramatic precipitation seasonality associated with tropical monsoon climates where it is consistently warm, but now we have this kind of variable precipitation pattern, which then produces a unique biome type, which we'll in a future lecture describe and explore biomes and biota in general. And then here, getting a little bit drier, a tropical savanna, also again, consistently warm, but tropical savannas, like pictured here, receive much less precipitation, and therefore their biota, as you would here, as we can see, is much different than a tropical rainforest. And so these become slightly drier, although a savanna now still a fairly humid climate. It receives enough moisture to support a decent amount of biomass. As we then transition from this warm and really wet to moderately wet tropical subcategories, we can move our way into the arid and semi-arid climate. So we went from A, tropical, to B, arid and semi-arid. And as you see here, a lot of our arid and semi-arid climates happen to fall right at the tropics of Capricorn and Cancer, and then a little bit further north, so 30 degrees north and 30 degrees south. And if you remember back to a previous topic when we were covering Hadley cells and those locations of the persistent subtropical high pressure systems that have persistently warm and dry conditions, they happen to be right about at 30 degrees north and 30 degrees south. And voila, we have subtropical low pressure, really dry, or subtropical high pressure rather, with low precipitation patterns. So warm and dry. And so now within arid and semi-arid climates, this B category, we can further subdivide using our precipitation and temperature extreme ranges, really based on kind of hot and cold, and then we're going to separate further on precipitation. And so again, I'm not going to expect that you know all these subdivisions for any quiz or exam. I simply want you to be able to compare among the major climates. But I do think it's important for us to explore these in a little greater detail, where we have hot, dry, so hot, low latitude. So these regions closer to the equator, like this dark region being the Sahara, that's kind of your true hot, dry desert versus there's a lot of the region around the world, like here in Utah, this picture from Awachimo Bridge, which I took many years ago, that are these cold mid-latitude deserts where they're cold for a portion of the year. So, for example, in the winter in southern Utah, it's actually quite cold and is often below freezing, at least at night or for many days or weeks and months in a row. However, the sun or the summers are quite hot, but these then really much different than something like Sahara Africa. And so you can see these kind of cold mid-latitude deserts often kind of bordering some of the hotter regions and some of them also due to elevation. And then this term steppe, and we'll kind of return to the term steppe when we look at biomes, but now this means it's semi-arid. And so whenever you see Steppe, that's an indicator that it's hot, and it might be hot at low latitude or these cold mid-latitude regions. And the steppe environment will support some vegetation. You might have sparse grasslands. And so it's not this incredibly lush and with lots of biomass grassland, but a steppe grassland is a semi-arid, kind of sparsely populated grassland. So moving a little further north or a little further south, depending on what direction you're moving from the equator, we can explore mesothermal climates. And so now compared to these arid and semi-arid, and then compared to our tropical climates, mesothermal climates have distinct warm and cold seasons. And so seasonality becomes more influential the farther you get away from the equator, at least for temperature specifically. And so we have distinct warm and cold seasons, as you can see, really kind of central and southeastern US, the entirety, including Florida up into Georgia, beyond over into portions of Texas and Oklahoma, are considered mesothermal. And then these regions around the world, both north and south of the equator, typically falling somewhere between 20 degrees and 60 degrees, which is a pretty huge range. And then some of these additional climate factors like the trade winds and et cetera, further influencing the location of some of these mesothermal climates. And so mesothermal climates can be further subdivided into humid subtropical. And so we have hot summers, really hot, and then Mediterranean. And really, anytime we see Mediterranean, it's kind of like a monsoonal climate in the sense that there are these periods of moist and periods of dry or even drought conditions. They're not quite as extreme as a monsoonal climate, but they very much have similar seasonality where there's a portion of the year that's dry and a portion of the year that's wet. And then here, more of the regulated marine or maritime climates. And so we have these kind of distinct seasonalities along the coastal regions, like Oregon, for example, submarine west coast. Moving further north and to some extent further south, but as you can see in this map, our microthermal climates of the world are really largely dominated all the way across the northern hemisphere. And now we're really thinking more limited from 35 degrees north up to 60 degrees north. Where again here in Marquette, we're at 46.5 degrees. And so we're perfectly situated in the middle of a microthermal climate, which is letter D, which is in fact where we are here in Marquette. And so now, as we experience in Marquette, we have longer cold seasons, at least compared to places like South Carolina, with limited warm seasons. We can further subdivide, and as you can see, there's a lot of subdivisions within our microthermal climates. Again, not expecting you to memorize or to otherwise, I'm not going to evaluate you on these subdivisions, but humid continental versus mild summers, hot summers. We have subarctic. And so really, as we move from south to north, it becomes more and more Arctic. And really, as that microthermal climate is warm enough in the summer to be considered microthermal, we'll call those subarctic climates all across the global north. So let's move into E, polar climates. And so in this case, we're going to separate it from highland climates, which are mountainous regions with very dramatic topography. But here, polar climates are non-mountainous areas that are northward or southward from some 70 degrees. And so from 70 to 90 north and 70 to 90 south. And these are characterized by long, cold winters with little precipitation. And so that's a unique part of polar climates that I think is maybe underappreciated or can be, even though there's this tremendous amount of snow and ice in our polar regions, there's actually very little precipitation that falls. And so they're often considered kind of like dry, almost arid or semi-arid in that sense. And so we have long, cold winters, but net precipitation, the total amount of precipitation that falls, is relatively small. And we can further subdivide polar climates between tundras and ice cap. And so, like this picture is an ice cap. However, in the future, we'll explore tundra, both climate and then biomes, where there are these kind of expansive regions with very limited vegetation because there's this really small growing season, but some of these regions, in fact, have just enough of a growing season to support what is considered tundra vegetation, which is highly stunted, very short and sparse. Okay, so now let's focus on highland climates, which is letter E. Sorry, I forgot to put an E right here, but our highland climate, or sorry, H. E is polar and highland climate, H, and so associated with large mountain ranges. And so influenced by temperature with altitude, and as you can see here, our Colorado Rockies, the Andes, the Himalayas, the Alps, these large mountain ranges of the world are considered to have highland climates. And so the unique thing of a highland climate is that it can supersede latitude. And so you could be in basically tropical locations, but if you're at high enough elevation, that highland system, that incredible elevation will supersede the factors being influenced at that latitude. And so within highland climate, they can be highly variable. Mostly, I just want us to appreciate the variation within a highland climate. And we'll come back to this and look at highland ecosystems in a future topic focused more on biomes. But like relative orientation, north facing versus south facing slopes, these latitudinal gradients, are you on the windward side or the leeward side? Variation within a day in mountain systems can be incredibly variable from hot and sunny to incredibly cold. Um, and so there's many environmental characteristics to appreciate about highland climates. Again, sorry, H is that letter. Um, moving now on to looking at past climates. And so we actually know quite a bit about past climates and past conditions on Earth. And so now I want us to think about how, or at least examine how do we know that? So does anyone or is anyone aware of how we reconstruct past climate conditions? Like, how did we know what life was like 100,000 years ago or 400,000 years ago or 800,000 years ago? And there are a few methods to reconstruct past climates, but the one method that we'll focus on here, at least on this slide, and again on future slides, is using ice core records. And so literally, and what's a kind of a unique thing about ice core records is we can compare ice that was relatively recently formed, like in the last 100 years or so. And what they do is they extract a core of ice. They can even extract the gas bubbles that are trapped in that core of ice and also melt the water that makes up the ice. And from the chemistry of that water and the trapped gas, we can even verify and corroborate with observations from places like Mauna Loa at Hawaii and other global scale atmospheric monitoring stations. And we can literally like match the data being recorded in the ice core records with observational data. Well, that period of time where it overlaps, where we have real observational data from places like Mauna Loa Observatory in Hawaii, with ice cores from around the world, including in Alaska and Siberia, or in the, sorry, Arctic Circle, is relatively limited. It's proven that this science is very sound. And so literally, again, you can melt the water, you can look at the isotopic ratios of hydrogen and oxygen, which allows us to estimate temperature with a pretty large degree of accuracy. And that ratios of isotopes, then we can get glacial ice from older and older. We can also do carbon dating. And so now there's these locations all around the world that have glaciers, and some of them have these incredibly deep, really old glaciers. And so we can carbon date, we can look at carbon dioxide concentrations trapped in gas bubbles and look at other conditions like isotopic ratios to reconstruct the temperature. And then again, we can go back in time, all the way back, and some of the oldest records that we have, in fact, go back to 800,000 years. I think this type of science is so incredibly fascinating and really highly rigorous. It is based upon chemistry and really on geology and physical geography. And so here again, our past climate reconstructions and something that we'll kind of come back to is focusing on some of these unique conditions that exist in Earth today that haven't at least existed in the past 800,000 years. So let's move on a little bit. So with some of these past climate reconstructions, both using ice cores as well as other methods, we can kind of separate them into short-term fluctuations. So think more in like the decadal cycle or hundreds of year cycle versus long-term fluctuations, thinking about like tens of thousands and hundreds of thousands of years. And you can kind of see this pattern of warm and cold and warm and cold. And these, at least more recently, are our major glacial advances. And so we can also look at the influence of glacial advances in our geologic record here. And here's our most recent glacial advance, and the one before that, and the one before that. And so we have these periods of long-term fluctuations, thinking like hundreds of thousands of years and perhaps like thousands and tens of thousands within them. But then we can even zoom in further and look at much shorter term fluctuations and how they're recorded in some of these proxy indicators, as we'll talk about here. And so beyond ice cores, there's other methods that we can use to reconstruct past climate. Among them includes the collection of pollen records, where survey teams that look something like this, which I've also done in wetlands, where you literally take incremental cores of peat, so organic soil sediments coming out of these wetland systems, and you remove them, and then you can look and literally you can extract the pollen that's occupied. You can then carbon date, and you can think about what types of plant species were present at certain periods in the past, even hundreds and thousands of years ago. And then based upon our knowledge of the distribution of pollen, you can reconstruct what the climate must have been like in order to support or inhibit rather other species. And so you can literally document like the presence or the arrival of species like sugar maple, for example, in the Upper Peninsula hasn't always been here, and it needs to be warm enough for sugar maple to exist. And so as you go further back, and we can go into wetlands even around Marquette, and you can like literally find, you go deeper and deeper, it's older and older, and there's no sugar maple pollen, no sugar maple pollen, no sugar maple pollen. There might be things like spruce and white pine, but then all of a sudden sugar maple pollen shows up, and you could carbon date that and say, okay, it was approximately 2,500 years ago when sugar maple arrived in Marquette. And because of what we know of sugar maple's habitat, that means the climate must have become increasingly warmer. And so that's one method. We use these proxy data again. So this is maybe not as direct as the ice core. You're kind of just inferring conditions based upon the presence or absence of pollen in these peat core records. More on a shorter time frame, you can look at trees. And so likely now we're thinking in like the decades to hundreds of years cycle, and you can look at their growth rings, and those growth rings will tell you a lot about the condition in that singular year. Was it a really favorable growth year? Was it warm and sunny and plenty of moisture? Was it drought, etc., or even potential like burn scars as well? And so you can use the study here, dendrochronology, studying tree ring patterns. And while this has a lot of evidence to support, and you can do a lot of interpretation, it still isn't quite as definitive as this ice core method. And again, so here, and I encourage you to stop right now, click and watch this "What do Antarctic ice cores tell us about climate change" video. What they tell us now, coming back, is you can extract these ice cores, and as I described and as the video describes, literally you can extract gaseous samples, and you can run those samples on gas chromatographs and other analytical instrumentation. You can literally quantify how much CO2 or methane or other compounds were in the atmosphere, match that with carbon dating, and voila, we like literally reconstructed the composition of our atmosphere going back up to 800,000 years. And then, without getting into too great of detail about isotopes, which I have done some isotopic research, myself with related to hydrology, we can simply, it's all about ratios. And so we can measure the ratio of heavy to light isotopes, and depending on that relative abundance of heavy to light oxygen or heavy to light hydrogen isotopes, it tells us a lot about what the temperature of the atmosphere is, and that is and can be proven both in laboratory as well as in field experiments. And so understanding these isotopic, or at least like literally analyzing these isotopic ratios, allows us to reconstruct past temperature conditions. So as described here, these ice core records, the oldest ones that we have or have access to that go back to 800,000 years. Many glacial records around the world go back to into the 100 to 400,000 range. And so there's only a few or fewer glacial samples that go back this far. But here in this kind of more recent time frame, we can look under really precise detail and more in some of the videos of glacials and like how glaciers form, literally there's snow that falls and then it gets solidified into ice. And then you have a kind of an intermediate period, and then the next year happens and you have another layer of ice and another layer. And actually in this kind of time frame of hundreds and thousands of years, you have like really good separation of singular layers that represent a singular year. And so our frequency of observation within ice core records is much higher in this more recent time frame. And then, as previously mentioned as well, going back into the 1950s, we can go back and actually like literally match the ice core samples with the same techniques with isotopes and with carbon dioxide and our gas chromatograph, and we can match those exactly with the measurements being collected in real time at Mauna Loa and other global weather and climate observatories to corroborate and verify these data. And so with that, one thing that is and has become quite alarming, at least in a 800,000 year time frame. If you look at this, this is literally the concentration of carbon dioxide in our atmosphere using ice core records going back, and it goes up and it goes down, and they really kind of coincide with these large, like 10 to 100,000 year cycles of warm and cold and warm and cold. And so if you look at it though, here were some of the highest peaks recorded about 300 to 200,000 years ago, and our highest peaks are right about at the 300 parts per million range. And so here, flash forward to near present, and so now we're thinking really in the last couple hundred years, we have increased global concentrations of CO2 upwards of 400, and currently we're sitting right around 430 parts per million, which looks like 130 parts per million more than in the past 800,000 years. And so this alone is highly verified evidence suggesting, or really proving, in my opinion, that humans have largely influenced our atmospheric conditions. And now where it then translates into is, how does this difference? Here's evidence that literally shows that we as humans have influenced carbon dioxide concentrations, because we can also literally like look at the carbon dioxide and where it came from, being combustion of fossil fuels, to show this increasing amount. But what does that actually mean for climate? And so this is where the discussion of climate change can be incredibly expansive. What I want and what I encourage all of us to do is really just tie it back into previous lecture content, thinking about radiation and storage and transfer of energy, and thinking about the fact that CO2 is a greenhouse gas. It's capable of storing and radiating energy. The more you have, the greater the greenhouse effect, which then leads us to believe that the temperature on Earth is increasing due to this increasing amount of CO2. And so here is the isotopic record then matching that. And so our ice core record also in the last couple hundred years showing that our temperatures are currently unprecedented, at least in the past 800,000 years. And so this is a big difference, and it is also very quite abrupt, the rate of change. And so this scale is much different than this scale. And so this rate of change is incredibly fast, also unprecedented. However, so that was this kind of like focus on how humans have influenced atmosphere and ultimately climate on Earth. However, as we go back further into the geologic record, there are most definitely large natural factors, both episodic, so very large events like volcanic activity, and then we'll next explore what's called the Milankovitch theory, also known as the Milankovitch cycle. But for here, appreciate that super volcanoes like Yellowstone and other super volcanoes around the world are so massive that when they erupt, they disrupt climates on a global scale. And so at an active volcano or sorry, a volcanic event from something like Yellowstone will have these like many hundreds, like decades and hundreds and thousands of years of fallout, if you will. And so these super volcanoes are capable of causing massive climate change. Um, so are asteroid impacts. And so large asteroid impacts now recorded in our geologic record are, and then further evidence with things like presence and then the extinction of dinosaurs linking with what's known as the Chicxulub crater in the Yucatan suggest that these asteroid impacts had incredible influence, way more so than this event of humans. What's different though is that was one singular event that had a pretty short, relatively geologically speaking, time frame. That eruption happened. It might have been active for, a year or years. An impact from an asteroid is incredibly specific. It happened, and then all of the fallout happens, and it took a really long time for the atmosphere to recover. What's different here is that isn't just this one like asteroid impact. It is this kind of like fairly rapid but consistent and doesn't seem to be changing condition of us adding CO2 into our atmosphere. So this is a mechanism of climate change, this increase in CO2. Volcanic activity is a natural mechanism of climate change. They have to be pretty big volcanoes. And then also asteroid impacts is a mechanism of climate change. These are all causes. Something that I just really think is fascinating and interesting is perhaps you were aware or you heard at some point in the past that this meteor or this asteroid impact that is known as the Chicxulub crater, which is near the Yucatan, is largely assumed to have resulted in such massive climate change that dinosaurs became extinct. And so this was this incredibly like Earth climate altering asteroid impact. And so this is in the hundreds of millions of years ago range. However, in a much older range, and so before the time of the dinosaurs, there was an even bigger asteroid impact. And that now I don't know the date off the top of my head, but I believe it's in the 1 billion time range. I'd have to look it up, but you could click on this link and read about it if you want. And that asteroid impact is called the Sudbury impact. And literally, if you're aware, Sudbury, Ontario is not very far away from here. And so just a little bit further north into the east than Sault Ste. Marie is Sudbury. And in fact, a long time ago, there was an impact that was even bigger than that Chicxulub impact. It was so big, in fact, that it sent pieces of earth flying. This kind of graphic does a good demonstration. So think about like throwing a rock into the sand, and then that sand or the dirt and the soil goes flying because you threw the rock. And so now think about this giant asteroid that hit, and it hit near Sudbury, Ontario, and then chunks of earth literally went flying in all directions. And some of those chunks landed here in Marquette. And so that's pretty darn far. It takes about 3 hours to drive to the Sioux, and I think Sudbury's another hour or two past that. So we're thinking like a 5 hour drive on a highway, and that this asteroid just sent pieces of Earth flying that far. And we're not even the farthest documented. Some of those pieces, which are called impactites, landed even all the way across into Minnesota. So pretty darn cool. If you want to find them, you can go down by the Dead River at the High Bridge where County Road 510 crosses the Dead River, and you can still uncover specimens of the Sudbury impactite that landed here in Marquette. Okay, I digress, and now we're coming back. So a major goal of this entire lecture is to focus both on human or how humans have altered atmospheric conditions that then are causing or at least an agent of climate change. But there are also very much natural climate change mechanisms, these two being really episodic or short term with drastic implications. However, there is this other natural form of climate change that is very real. And so let's explore that now. And this has everything to do, I'm going to go back with these large cycles of being warm and cold and warm and cold. And so why are there these kind of approximate 100,000 year cycles of warming and cooling? It has everything to do with what's known as the Milankovitch theory, which also is known as the Milankovitch cycle. There are three components to the Milankovitch theory. The first component is what's known as orbital eccentricity. It is the variation in the shape of Earth's orbit and how it influences the amount of radiation received from the sun on planet Earth. And so, as we previously explored in this class, our orbit around the sun is largely elliptical, and we're tilted and we're spinning, but we're revolving in this orbital path. However, you track this orbital path over approximately 100,000 years, and the orbit goes from very elliptical to nearly circular, not quite, but pretty darn circular, and then back to elliptical at a 100,000 year variation. And so that in and of itself then is causing there at this scale to be different amounts of radiation received on planet Earth and the balance of energy. And so that's one way that natural climate variation is influenced by the first part of the Milankovitch theory. The second part of the Milankovitch theory is called tilt obliquity. And so this is where, and as we learned here now today, Earth is currently 23.5 degrees tilted relative to perpendicular. Again, if the sun was here and the Earth was here, and this is perpendicular, the Earth is tilted at 23.5 degrees, where our magnetic north and south pole are tilted, right? However, that tilt does not stay the same, and that tilt at about a 40,000 year cycle goes from about 22 degrees all the way up to about 24.5 degrees, and it goes back and forth just like that. And so as we learn, that amount of tilt has a lot, really can have tremendous effects on insulation, on the amount of radiation received at Earth's surface and on a global and as well as kind of a regional or local scale. And so tilt obliquity and orbital eccentricity are overlapping, each of them influencing radiation on a global scale. And then last but not least, there's three parts to the Milankovitch theory or the Milankovitch cycle. The last part is called orbital precession. And so how this works is if you've ever spun a top, you watch the top as it's spinning really fast, then the handle of the top stays kind of upright. But then as the top starts to slow down, the handle kind of does this wobbling motion where the handle kind of like moves around. And if you look straight down, you'll notice that there's this precession, as it's known. That's exactly also what's happening to Earth. And so what another part that we learned is if this is the sun and this is Earth, we're tilted, and that as we revolve around that sun, our tilt doesn't change. But at this kind of more 10,000-ish to 20,000, so between 10 and 20,000 years, literally our tilt will kind of like do this, which effectively would be the reverse, where our northern hemisphere for us currently would be tilted away during what is now our summer. And so we would like literally reverse that. And so similarly here, all three of these are co-occurring. They're all occurring. These are each individual cycles that we can like literally measure with astronomical precision or using astronomical methods. And so these are very well documented and very real cycles that are occurring, and each of them influence radiation, and they overlap, and they happen to overlap based upon the models constructed from these observations. We have estimates as to the periods of time where we would expect the least amount of radiation received on Earth and periods of time where you expect the most amount of radiation received. And it happens to occur at approximately 100,000 year cycle. And so some of these like smaller cycles and then bigger cycles, we can reconstruct using what's called the Milankovitch cycle. So check it out, this video featuring Professor Richard Alley describing in his own very unique way what the Milankovitch cycle and how it is and how it affects temperatures on planet Earth. So last but not least, now we've talked about major factors that influence climate. We've talked about the classification of climates using the Köppen climate classification system. We've now examined how scientifically we can reconstruct past climates. Now let's think about how we as humans are influencing climate and what potential future implications exist based upon these influences that we're having on our climate. It has, as we've talked now multiple times, a lot to do with carbon, not just carbon dioxide, but as well as methane. But let's just focus on carbon dioxide as well as carbon cycle in general to better understand where carbon exists on Earth, how it's cycled, and then perhaps how we as humans are interfering with a natural carbon cycle. So, as we previously learned, carbon dioxide is a variable gas. It varies in our atmosphere. It also is a greenhouse gas capable of storing long or shortwave radiation and then emitting that as long wave radiation, so counter radiation. And it is essential to all life on Earth through processes like photosynthesis. Carbon is everywhere, and so carbon can be stored and it can move between what we call reservoirs, like areas that carbon is stored. We have carbon, plants have carbon, the materials we use have carbon, soil has carbon, the atmosphere has carbon, the ocean has carbon in many different forms, both in gaseous and as physical. And so now we can look at then further separate these carbon reservoirs that exist in the atmosphere, in the ocean, in deep in our lithologies and our geology, and we can separate them into what we largely call active and inactive zones. And so active zones really are like living things in soil, atmosphere. It's where carbon on at least on a geologic timescale is largely active. It's going from one reservoir to another, and there's lots of exchanges between. And so think about on a daily basis with photosynthesis, you have carbon dioxide in the atmosphere being assimilated via photosynthesis by trees and being integrated into their tissues. And then that tree exists, but really maybe for hundreds of years. And then it decays into the soil, it breaks down, and then it returns to the atmosphere. So all within, and that could even be shorter, it could be days to hundreds of years, you have this carbon cycle. And see, these are very much active when compared to geologic timescales where we have carbon trapped in rocks and carboniferous rocks as they're known deep down under the earth. And in those places, carbon can be stored for incredibly long periods of time, like hundreds of millions of years, for example. And so these are our inactive zones where carbon is largely stored in these deep ocean sediments and deep ocean lithologies, as well as underground here in these inactive zones. However, we as humans are most definitely interfering with this natural carbon cycle. And so, how are we doing that? We're doing it by extracting fossil fuels. And so, these carbon reservoirs in the form of coal, natural gas, and oil that are trapped deep beneath Earth's surface, which on large geologic timescales will cycle all the way through. However, they should, or without human interference or intervention rather, they would just continue to be trapped in those long inactive zones. We are rapidly and extensively extracting these inactive carbon from the ground and under the ocean, bringing it up to the surface, and then largely combusting it for many different reasons to produce energy, and then that combustion of this inactive carbon is literally going directly into the atmosphere. And so we've largely like interrupted the natural cycle of active and inactive, where we're removing this incredible amount of inactive carbon and now kind of like literally directly injecting it into one of the active reservoirs being our atmosphere. One thing that I think is really cool just about fossil fuels in general is that it all used to be living, like it was living organisms. We wouldn't have fossil fuels if we didn't have life. And so one thing that I like to kind of like think about or like conceptualize about fossil fuels, like when we extract natural gas from these deep reservoirs, that natural gas, the oil and the coal all used to be living organisms. And so something like coal, for example, may have existed in something like the Florida Everglades, this giant like state scale swamp that then now imagine the entirety of the Florida Everglades gets buried and then gets sunk underground and trapped. And then it gets compressed and it turns into probably all oil, gas, as well as coal. But really, like when we're extracting coal from the ground, you're literally extracting like a paleo version of the Florida Everglades. And then we're using it to power and generate electricity, among other things. And so all of these they were at one time an organism that died, and now that carbon is trapped, and we're extracting it, and some of that carbon being incredibly old. So a little bit more, just kind of like touching on humans and climate change. And so we are extracting this inactive carbon, we're combusting it for the most part, and it's then going from this inactive zone and it's kind of like immediately entering our atmosphere. And so we can look at our carbon dioxide concentrations and track it back to kind of the time of the Industrial Revolution and track our increase of carbon dioxide concentrations from around 280 to 300, which if you remember in the last 800,000 years, these were the highest concentrations ever recorded on Earth, right about there. And so then flash forward from about 1900 to 1910 to present, where we've now increased our carbon dioxide concentrations. And in fact, today, hovering just shy of 430. And so now we've like really dramatically increased carbon dioxide in our atmosphere. And so we know that part is true. We can like literally quantify it. We can measure it. We can also like measure and track temperature, but this is still a really small range of time when compared to the Earth, which is like over 4 billion years old. And so as much as we know, there's also things we don't. And so there is a subject of heated debate. And so my goal for this lecture and for us as we explore climate and climate change is to appreciate natural climate variability from things like the Milankovitch cycle, as well as from episodic events like volcanoes, as well as impacts, but also to appreciate that we as humans are combusting incredible amounts of fossil fuels and that we have definitely altered carbon dioxide concentrations. What does that mean for temperature? We are observing these rapid increases in temperature, and in 800,000 years, Earth now is warmer than it ever has been. But that doesn't mean it's warmer than it ever has been for 4 billion years. And so this is kind of like where some of this debate comes in, and where does the evidence align, and where are the misunderstandings, if you will. And so that's something I'd like to at least focus on here and moving forward is there are elements that we know with scientific rigor and methodology, and then there's aspects like sea level rise, and then what does that mean? And flashing forward to 100 years, what does that look like? Or the warming Arctic, and so there are immediate influences that we are already measuring. What becomes a little less certain is what will happen 100 years from now. And so scientists the world over are trying to figure that out, and they create what are known as general general circulation models, which are among the most sophisticated mathematical models on planet Earth, and they're taking all of this past climate data and they're using it to project the future, and they have different scenarios which likely or which then are related to different amounts of carbon dioxide and what we know, like literally physical and chemical interactions of CO2. We can estimate how much radiation that increasing amounts of CO2 will trap. And so these are our future climate projections under kind of like best case and worst case scenarios of increased warming. And so it has been warming. It's going to continue to warm because we're continuing to extract fossil fuels and combust at large scales. And perhaps with some future or maybe near future technology, we can start to kind of mitigate some of these combustion sources. And so that's kind of where the future is headed, or what we think, where we think it's headed. What do we actually know, though? One other documented evidence now using both ground-based as well as remote-based measurement and then linking those measurements and observations with glacial cycles is that global temperatures on planet Earth on average are warming. They're only like on a global average, they're just slightly above average. However, this is enhanced in the northern and southern latitudes. And really, since there's this enormous amount of land mass from 70 degrees north, this is where it's being more pronounced. So another implication, or literally like an outcome of CO2 and increased temperature, is that temperature is increasing at incredibly fast rates in the Arctic. And so we would expect, like, let's say a 1 or 2 degrees Celsius temperature increase in kind of like mesothermal climates. However, in Arctic and far north microthermal climates like here, we're already observing from normal an 8 degree Celsius increase, meaning average temperatures on an annual basis in this part of the world are already 8 degrees Celsius warmer than they've been in a very long time. And so, what my point then is, it's enhanced in different locations around the world, and we can actually then monitor and observe this as well. So, if you want to learn a little bit about how we can maybe combat climate change and think about the role of soils within climates and climate change, I encourage you to click and watch this video. So a little bit about climate feedbacks and just like what is a feedback in general. So a climate feedback in this case is an indirect or secondary change within the climate system. What does that mean? So I'm just going to provide one example here. So now let's say we're kind of going back. So we've added a little bit of CO2. Temperatures have increased. And as I just said, temperature increase is most pronounced in northern latitudes, so Arctic, polar, and maybe northern microthermal regions, the far north, right? So what does that mean? We have lots of ice caps and glaciers extending Greenland and the Arctic Circle. We have all these glaciers in the Arctic North, and that looks like snow and ice, which has this incredible amount of albedo. Our glaciers are rapidly retreating because of this warming climate condition that we're experiencing. So now what does that look like? It means there's less albedo. And so here, like step one, the initial influence is the CO2 and the climate warming being forced by this increased greenhouse gas. But the feedback here becomes what some scientists worry becomes like a runaway effect, where as more and more glacier melts, there's less and less albedo, meaning there's more and more absorption of the sun's radiation by Earth, by the water, as well as by the land. And then it's being stored and re-radiating energy. And then that's going to cause a warmer climate, and that's going to translate into more ice loss. And then the connection continues, and that's the feedback loop, as here presented with ice caps and glaciers. Some very similar concerns with videos we may have previously watched and video that we will watch in the future, kind of like thinking about soils and going back to this role of soils. There's an incredible amount of carbon stored in soil in the global north, especially in the northern hemisphere in this range. And this area is experiencing incredible rates of warming, which means it's breaking down this once frozen carbon material that was stored in the soil, and more of it's being released. And so then there's more CO2, and the more CO2, the more warming, and that is another form of a feedback loop. And so here the future is unknown. It really is uncertain. We're kind of just living this experiment, if you will, as we are. So now how does that affect our lives? And so, perhaps you can like simply just think about temperature. And so if global temperatures are rising, that means warm places are getting even hotter, and some places are fairly inhabitable as they are because they're already really hot, right? And so if warm places get hotter, that can look like more heat stress and stroke, and that could be, affecting labor. And think about how many people work out in the environment, all the farmers of the world, as they're working in these conditions. And as they get warmer, it becomes more hostile, if you will, more difficult, and likely more human health related issues just with increasing heat conditions. Here, then, kind of focusing, and then I'll focus both on temperature and precipitation in this example. And so we're going to narrow our focus into the Amazon a little bit. One thing that I like to just appreciate about carbon cycle and greenhouse gases, so carbon and methane emissions, is that there is a tremendous amount of carbon and methane that's generated from the burning of fossil fuels. So our combustion, so transportation vehicles, energy from our power plants, construction, etc. And so there's a tremendous amount of greenhouse gases emitted from these combustion sources. However, there's also a tremendous amount of greenhouse gases emitted from converting land, so deforestation, land use change, and then just from agriculture activities, literally like enhancing what you would expect otherwise. And so as we add pigs and cow and cattle on the landscape, that can contribute to this like increased amount of greenhouse gas emissions. However, what I want to focus on, appreciate the sheer magnitude of the Amazon region. And so this biome, Amazonia, occupies this huge portion of South America. It is massive. Like it is, maybe not the size of the US, but pretty darn close. Um, and so there's this huge area that is the Amazon that's experienced tremendous deforestation. And so you took this tropical rainforest and we've deforested it on incredible scales. And we've converted these tropical forests to largely agriculture and livestock production. And so now they're incredibly different biomes. And by doing that, we have altered the greenhouse gases being emitted by that landscape. But moreover, thinking about regional and local climates, this has had this really very localized in South America. And watching the video will help you kind of understand both what we're doing, or what places in the Amazon are doing to kind of combat deforestation, but also appreciating what happened to climates in this region. So areas and communities that had existed before deforestation had been adapted to certain temperature and precipitation conditions. If you wipe out an entire forest, you've dramatically altered like the amount of evaporation and evapotranspiration that's existing. You're altered dramatically and altering the amount of radiation that's now being stored and received by Earth's surface and then re-radiated. And so literally like climate conditions throughout the Amazon have been dramatically affected, being warmer and drier post deforestation. And so here, kind of more like a regional emphasis on how we as humans can influence climates, and in this case, being on more like a continental or subcontinental scale, but also then generally just contributing to our humans' influence worldwide, with added greenhouse gas emissions. So there's one spotlight, if you will, and another spotlight, as there are many to focus on. And I guess we could kind of keep going down and talking about more and more. But another one that you have likely at least encountered at some point in your life is this discussion of sea level rise. And so as our temperature of planet Earth is getting warmer, and as it's getting exceptionally warmer across the north and south, so North Pole, South Pole regions, where most of our ice caps and glaciers are occupied, that melting ice then is being added to the ocean, and it's literally translating into already measurable increases in sea levels. And so we can quantify how much ice is like literally contained in somewhere like Greenland or in some of the large ice shelves, as you can watch these videos to more uncover some of our current state of knowledge of um, ice packs and their vulnerability to warming. And we can think about like literally as some of these large ice shelves are likely going to separate and eventually melt into the ocean, what that would mean for translated sea level rise, and then we can look at the global population, and really the majority of the world's population lives somewhere near sea level. And so there would be this incredible influence, and some of this is already being felt in places like the Maldives. So certain regions that are very low topography at sea level currently are already being displaced and relocated due to what we've already observed of sea level rise, where again, kind of going back, the future, sorry to go back, the future's untold, but it looks like it's going to get warmer, which means there's going to be more ice melting, which means there's going to be more sea level rising, and some of these videos then highlighting some of the human welfare impacts for all of our coastal communities. Storm damage is greater, and so even if your community still remains above sea level, now that sea level is a little higher, it means that each of the storms is now a little higher, and those waves and those um, detrimental or devastating events like big events or hurricanes and wave damage are now more pronounced because the entire ocean is just that much higher. So I encourage you to watch both Antarctic Melting Journey to the Doomsday Glacier, which both of these videos contain some really, I think, kind of cool documentation of science and what we're doing to monitor glaciers the world over. So that's video one by the BBC, and then the second video being what's happening to ice sheets. And so here from Columbia University, another great video focusing on our interaction of climate and glaciers. So last but not least, I want us just to kind of like take a moment and discuss this, maybe to yourself, but with this whole discussion of natural climate change and human-induced climate change, I want you to think about it for yourself. And so what do you think based upon this lecture, what you know, what you've heard from the news, what you can find online? Do you think humans are causing climate to change more rapidly than what would be expected based upon our past climate reconstructions? Meaning, is are the outcomes like carbon dioxide, are these influences of humans causing climates to change in a way that we would not expect based upon the Milankovitch cycle or natural climate change? So I want us just to mostly appreciate that there's natural climate variability, and then I want you to think about it in your own way. Do you think that we as humans are changing climate? What kind of defensible scientific exist that would either support or contradict this? Like maybe you think climates are not being influenced by humans. So I encourage you to dig in, like look for the scientific evidence to support whether climates are or aren't being influenced by humans. And then secondly, really the second part can be answered irregardless whether you think you think climates are being influenced by humans, because natural climate change exists and it is huge. It is very dramatic, these big glacial cycles and warming periods. And so there is natural climate variability. And so in the scope of both natural and or human exacerbated or human influenced, how does climate change influence human health, human welfare? What are some of the implications? We've talked a little bit about them with sea level rise and with increasing temperatures, but those are just a few among many potential implications that climate change has for human health and welfare. So I encourage you to dig into all of these resources, both the videos and then many of these slides. As you'll notice, I've included intentionally some hyperlinks to like New York Times articles and YouTube videos about the Maldives and other all the way through here. Here's a Nature Science article containing additional. So I kind of encourage you to dig into some of these references and citations sprinkled through the lecture to better understand climate change, and how it influences humans on planet Earth. With that, Dr. VG is signing off.